Okay. So let us move to what is this pooling is all about. So before that, we have seen the equivalent representation, right? And the as we have seen that there is a gap, and the we have also noted that the equivalent is not invariant, correct? And that is the place where exactly why we need a pooling, and that is going to be our current topic. So pooling, we also it is called as a shrinking the feature map. The pooling takes a feature map and divides it into the small regions, reducing each region to a single number. So before we are going to the working example, we'll first understand conceptually about why we had ever want to throw the information away like this. Correct? So after a convolution layer, we have a production of the feature map. So we typically don't care about the exact pixel perfect location of the detected feature. We mostly care about whether that feature is present in a general area and roughly where. So pooling is the mechanism that lets the network start being deliberately sloppy about the exact position in a controlled way, which in turn which in turn turns out to be the exactly what's needed to eventually get from the equivalent to something closer to invariant, right? So here we have, you can see in the example, we have the 4 by 4 feature map divided into four 2 by 2 colored blocks. So using a max pooling with a 2 by 2 window and stride of 2, we take the maximum value from each block. So the purple block gives us 6 as the value, the first block. The teal block gives us the 4 as the value. The coral block gives us the 4 value, and the amber block, which gives us the 3 value, which produces 2 by 2 output on the right. So now there is the important invariance check on the right side of this slide, you can see. So if the strongest value, the 6, has instead appeared anywhere else inside the same purple block, correct? The output would be still 6. The final result doesn't change even though the strong feature moved position within the block. That's the local translation invariance demonstrated numerically. Right? So this is the key mechanism. What does it say? It says that by summarizing a small neighborhood down to just its strongest activation, pooling makes the network's output robust to small shift, jitters, or the noise in exactly where the feature appears, as long as it is still roughly in the same neighborhood, right? But of course, there is a real cost here too. That is like a top left block held four numbers, like it's 1, 3, 5, 6. I hope you all are able to see in this screen. And the max pooling keeps only one of them, discarding the rest completely. That's 75% of the information in that block is simply thrown away, right? We are just taking the max number and the remaining numbers we are just discarding because we are trying to draw a precise boundary around an object, not just say whether the object is present. So this discarded information can genuinely hurt in performance, which is why the segmentation architectures often avoid heavy pooling or use the spatial techniques to recover the lost spatial details. So this is why we have the pooling, and then the consecutively we had seen the disadvantages of pooling. Now we'll move to the types of pooling. Here you can see there are the types which are listed. These are the 5 types. The first one is a max pooling. Then we have the average pooling. Then the global average pooling. We have the minimum pooling and L2 not pooling. Now let's see what these all are one by one. So there are several types of pooling we should know. So the max pooling, the first one, the most common takes the maximum value in each region and keeps the strongest signal. The intuition is that the strongest activation is usually the most informative one, since it represents the location where the filter's pattern was most strongly present. Right? So the average pooling takes the mean instead of giving the smoother results that they retains more general or the background information. It's less aggressive than the max pooling and is useful when we want to preserve overall texture or intensity information rather than just the single strongest spike. Then the next we have is the global average pooling. I hope you are able to see there is a global average pooling. So it's a special case worth understanding here because it averages the entire feature map down to a single value per channel. So it collapses the spatial dimensions completely. So conceptually, this transforms each filter's entire feature map into one number that essentially answers the questions on average across the whole image. So it tells how strongly was this particular pattern detected. It's used in the modern architecture specifically to replace the use fully connected layers, which we will see in the real problem of with the AlexNet later on. So instead of flattening a large picture map volume and feeding it into an enormous dense layer, we can just average each channel down to one number and feed those numbers directly into the classifier, saving an enormous number of parameters. Then we have the mean pooling. You can see here, there is a mean pooling. So what does this mean pooling do? So mean pooling takes the minimum value and is rarely used, mainly when the absence of the feature is what matters. So for instance, suppose I wanted to detect the darkest point in the region rather than the brightest one. That's the simple example. Then we have the L2 norm pooling. The last which is stated here is L2 norm pooling. So this pooling takes the square root of the sum of squares in the region. So occasionally used because it gives the smoother gradients during the training compared to the sharp, non-differentiable at point behavior of the max operation. So that's all about the types of pooling. Now let's move to the next topic, that is the variant of the basic convolution. So over here, each variant fixes one specific limitation of the plane convolution, and we will see these variants one by one. So the plane convolution has its own limitation, and each variant we will be looking here, we are about to cover fixes one specific cost. So strided convolution lets the filter jump more than one pixel at a time with a 7 by 7 input, a 3 by 3 filter, and a stride 2, we get a 3 by 3 output directly, meaning the convolution itself does the downsampling instead of needing a separate pooling step. Right? So that's the feature of the strided convolution. Conceptually, what does it mean is that the network learns how to downsample since the filter weights themselves are trainable rather than using the fixed non-learnable rule like taking a maximum. So some modern architectures prefer this because it gives the network more flexibility in deciding what information to keep or discard during the downsampling. Then we have the padded convolution. So this padded convolution adds a zero padding around the border, which preserves the output size and makes sure border pixel gets treated as fairly as the center pixel. So our earlier 5 by 5 example with padding 1 stays 5 by 5. So we already discussed why this matters. Without it, a deep network shrinks too fast and border information gets systematically underrepresented. So that's my padded convolution. Then the last one is the dilated convolution or the across. So this convolution inserts the gaps between the kernel elements. What does it mean is, say there is a 3 by 3 filter with dilation 2, we actually see 5 by 5 area of the input, but still only uses 9 weights instead of the 25. A true 5 by 5 filter would need. So think of this as a filter with a whole sponge in it. So it samples every other pixel instead of every pixel, letting it cover a wider area of the image without any increase in the number of learnable weights or in the computational cost. So this lets the network grow its receptive field quickly without adding parameters, which is especially valuable in the task like this semantic segmentation, where the network needs to understand broad context around each pixel while still producing a dense pixel level output. So that's my about the variants of basic convolution. We have few more variants. Let's move ahead and then look at this remaining variants also. So we will continue with the remaining variants. So there is a depth-wise separable convolution. Now this splits a standard convolution into two cheaper steps, a per channel depth-wise step and the channel mixing point-wise step. So let's understand why this split saves so much computation. A standard convolution filter has to simultaneously learn a special pattern and how to combine the information across channels. So all in one operation, which multiplies the cost of both together. So by separating these two jobs, so first applying a small spatial filter independently to each channel and then using a cheap one by one convolution just to mix the information across channels. So we do almost this same job for the fraction of the cost for a 5 by 5 filter, going from 3 channels to 256 output channels. A standard convolution needs 900 to 19,200 weights, but this separable version needs only 843, roughly 23 times fewer. So, which is exactly why mobile and edge devices architectures like MobileNet uses it. So, as you can see that this depth-wise separable convolution is used mostly in the mobile network. So, because the phones and embedded devices have very limited compute and the battery budgets, right? Then the next one is one by one convolution. Now, this one by one convolution acts only across the channels, not across the space. It used to cheaply change the number of channels, going from 192 to 32 channels, cost just 6144 weights with a one by one filter versus 55,000 to 96 weights if we used an unnecessary 3 by 3 filter for the same job. Then conceptually, a one by one convolution is really just a small, fully connected layer applied independently at every spatial position. So mixing the channel information at that one pixel location without looking at any of its neighbors at all. So which is exactly the right tool where the spatial mixing is not needed. You just want to compress and expand number of feature channels cheaply. So then the finally we have the transposed convolution and is a learnable form of upsampling, essentially the reverse of the strided convolution. So taking a small feature map and expanding it back up, which is essential for the a task like the segmentation or the image generation, where we need to recover the spatial resolution that earlier pulling of the strided layers through away. So unlike a simple upsampling methods that just copy or interpolate pixels values, transpose convolution has learnable weights. So the network can learn the best way to fill the expanded space based on what it has learned about the structure of the data. So in short, we can say that the stride avoids a separate pooling step. So padding avoids losing border information. So the dilation avoids the cost of the physical larger filter. So depth-wise separable and one by one convolution avoids the heavy computation, and the transport convolution reverses downsampling when we need the resolution back. So this is what about the variants of the basic convolution. And then we will now start with the new topic, which is the basic architecture of CNN.